Hello everyone and thanks for watching Edupedia World videos. I am Manish Agrawal and today we'll continue our mole concepts next session. In this session we'll start with percentage compositions. Okay, we'll see what they mean and we'll understand what are different ways in which we calculate percentage composition. First, the term percentage composition. See, percentage composition is made up of two different words, percentage and composition. Alright, so when I say percentage, it simply means you have to evaluate the quantity with a base of 100. So basically whatever ratio, whatever fraction you calculate, just multiply that fraction with 100 and you get the percentage. Alright, that's pretty simple. And the word composition. Now when I say composition of a substance or composition of a mixture or composition of anything, alright, so composition implies two things. First, you need to enumerate the constituent parts of that substance. Alright, for example, when I say what is the composition of your drinking water, so first you have to identify all of the components in your drinking water. So that will be H2O, maybe minerals of sodium, so Na, maybe calcium carbonate, that is CaCO3. So first you name all the constituent parts of the substance. The second part of calculating composition is, or the meaning of composition includes the amount of those substances. Alright, so it's not enough to just identify the constituent substances, but you also need to find the amount of each of that substance. So percentage composition would include amount of each of the constituent parts in percentage forms. Okay, so let's see what we exactly mean by that by studying the formula for calculating percentage composition. Okay, so let's first talk about percentage composition in a mixture. Okay, a mixture is what? A mixture is nothing but when you take two or three substances, two or more substances, okay, together in a single container. Okay, you mix them and form a homogeneous whole. So that is a mixture. Okay, so mixture is nothing but when you mix two or more substances together, what you get is a mixture. Okay. So percentage composition in a mixture can be calculated in two different ways. Okay, first we can calculate percentage by mole, and next we can calculate percentage by mass. Okay, so let's see one by one what each of this means. So when I talk about percentage by mole, I mean what is the molar composition of that mixture. Okay, percentage by mole means molar composition of the mixture. That is, if I have been given 2 moles of the substance, then I need to identify out of those 2 moles what is the amount of, or what is the moles of each of the constituent part of that mixture. So let's see the formula. Percentage by mole is equal to 100 into a fraction, some fraction which we'll see what it is, and percentage by mass similarly will be 100 multiplied by some fraction. Okay. Again, percentage by mole is molar composition, percentage by mass is mass composition. Okay, so in this case, in percentage by mass, I need to know what is the mass of each of the constituent given the fixed mass of mixture. Okay, so percentage by mole. Percentage by mole is calculated as 100 multiplied by the fraction. The fraction is given moles of substance divided by total moles of mixture. For example, let's say I have 2 moles of a mixture of water and ammonia. Out of those 2 moles, 1.5 mole is water and 0.5 mole is ammonia. So together they make 2 moles of mixture. So now if I have to calculate the percentage composition, then first I identify the constituent substances. So the mixture contains 2 different substances. One is water, one is ammonia. Now moles of water is 1.5. So given moles of substance means given moles of water. So 1.5 divided by total moles, that is 2. So 1.5 divided by 2 multiplied by 100 will give me percentage of water in my mixture. Similarly, 0.5, that is given mole of ammonia. So 0.5 divided by total moles, that is 2 multiplied by 100, will give me percentage by mole of ammonia in the mixture. Okay. Similarly, percentage by mass is 100 multiplied by given mass of substance divided by total mass of mixture. So the concept behind both is the same. Only difference is in one case we use moles and in the other case we have to use mass. So again, I have the mixture of ammonia and water. This time I need to know the total mass of the mixture, and I also need to know individual masses of water and ammonia in the mixture in order to calculate their mass composition. Okay. So let's see this again through an example. Say you have been given a sample of air. Okay. Now air has lot of different gases in it. Let's say in our sample there are three major constituents of the air. First is nitrogen, then oxygen and CO2. You have been given molar composition of each of these gas. Molar composition means I am talking about percentage by mole. So you have been given that your air sample has 78% by mole of nitrogen, 21% by mole of oxygen and 1% by mole of carbon dioxide. Okay, so now you have to calculate individual moles of oxygen and CO2. Okay, you have to calculate moles of oxygen and carbon dioxide gas in 5 mole of air sample. So you have to calculate individual moles of oxygen and CO2 given that total number of moles of your air sample is 5. Okay, and then you also have to construct a similar table for composition of air by mass. So you have to solve two parts. First you have to calculate individual moles, and then you have to calculate molar, instead of molar composition, then you have to calculate mass composition of your air sample. So let's see how we are gonna approach this question. So first, you know that you have 5 moles of air. Next, what we have been given is that we have 78% N2 and we have 21% O2 and then we have 1% CO2. Alright, this is the molar composition of your air sample, and air sample is 5 moles. Okay, so let's directly use the formula. So formula for percentage by mole is given moles divided by total moles multiplied with 100. So percentage by mole of nitrogen in air is equal to 100 multiplied with a fraction. What is that fraction? Moles of N2 in your air sample divided by total moles of air. Okay, this is what your formula is, total moles of air. So you have been given percentage by mole of N2 is 78%. Let's substitute the values. So 78% is equal to 100 multiplied with moles of nitrogen. Let's say moles of nitrogen is N1. Okay, let's say that variable is N1 because we do not know its value. Let's call it N1. And total moles of air is 5. Total moles of air is 5. So this gives me N1 is equal to 78 multiplied by 5 divided by 100. Okay, so this is 3.9 moles. This is 3.9 mole. Similarly, you can calculate percentage by mole of oxygen. So percentage by mole of oxygen in your air sample is 21%. So this is equal to 100 multiplied with moles of oxygen, let's call it N2, divided by total moles of air, which is 5. So this gives me N2 is equal to 21 multiplied by 5 divided by 100. Okay. Similarly, I can calculate percentage by mole of CO2, which again is given to us, and it is equal to 1%, and its formula will be 100 multiplied by moles of CO2 in your air sample, let's say N3, divided by total moles of air, that is 5. So this gives me N3 is equal to 1 into 5 divided by 100. So these are moles of CO2 in my air sample. So this answers the first part of question. We now have moles of oxygen and we also have moles of CO2 in our air sample. Okay, and we also calculated moles of nitrogen. We don't need this for the first part, but we will need this for the second part of question. Now in the second part of question, you have to construct a similar table. Okay, basically you have to construct molar composition table, mass composition table for your air sample. So instead of these percentages, the answer might have different percentage as their answers, because these are molar percentage. They need not necessarily be same as mass percentages. Okay, so let's see how we are gonna construct that table. First we had calculated moles, so let's write the moles of each of the samples. So N2 was 3.9 moles in our air. N2 was 3.9 moles. O2 came out to be 21 multiplied by 5 divided by 100, that is 1.05 mole, and CO2 came out to be 5 by 100, which is 0.05 moles. Okay, so if you add them, you'll see that total moles will come out to be, they have to come out to be equal to your moles of air, which is 5. So 3.9 plus 1.05 plus 0.05 will give you 5 mole as the answer. Okay, so you can verify your calculations using this. At total moles, once you have calculated individual moles, you can check their sum and see if it is equal to total moles of sample. Okay, in this case 5. So now let's move on to our second part. You have to calculate mass composition. Now just like percentage by mole, we have the formula for percentage by mass. We don't need this anymore. Let's get rid of that. So now percentage by mass. Percentage by mass, let's say of N2, percentage by mass of N2 will be 100 multiplied with fraction. This time fraction will have mass of nitrogen divided by total mass of air. Alright, so percentage by mass of nitrogen will have 100 multiplied with mass of nitrogen divided by total mass of air. Okay, similarly, percentage by mass of oxygen will be 100 multiplied with W2. Okay, mass of oxygen, let's say it's W2 divided by total mass of air. Similarly, we can calculate percentage by mass of CO2. So first let's calculate W1, W2 and W3, that is individual masses of the gases in our air sample. So W1 is equal to mass of nitrogen. Okay, and how can we calculate mass of nitrogen given moles of nitrogen? We use the formula. Okay, formula we studied in our last session. What is that formula? That moles, that is N1 moles of nitrogen is equal to mass of nitrogen divided by its gram molecular mass. Okay, so this implies N1 is 3.9 is equal to W1 divided by, what is the gram molecular mass of nitrogen? 14 plus 14, 28 gram. Okay, I am not writing it in detail because by now you should be able to do it by yourself. So nitrogen N2 gas will have 14 plus 14, 28 gram as gram molecular mass. So 3.9 is equal to W1 divided by 28. So this way I can calculate W1 is equal to 3.9 multiplied with 28. Okay, so that will come out to be around 109.2 gram. Okay, this is the exact value actually. Similarly, we can calculate mass of oxygen in the air sample. Again, N2 is equal to W2 divided by gram molar mass of oxygen. What is the gram molar mass of oxygen? O2. So 16 into 2, or 16 plus 16, that is 32 gram. So this gives us W2 is equal to, N2 is 1.05. So 1.05 multiplied with 32. Okay, this gives us 1.05 multiplied with 32 as the mass of oxygen in a air sample. This will come out to be 33.6 gram. And similarly we can calculate for CO2. Again, W3 divided by, now what is the gram molar mass? Okay, what is the gram molar mass of CO2? Carbon has gram atomic mass of 12. So 12 and O2, that is 16 into 2. So 12 plus 32, which is 44. So gram molar mass of CO2 is 44. This gives us that weight of CO2 is 0.05 multiplied with 44. Okay, and this value will be equal to 2.2 grams. Okay, this comes out to be equal to 2.2 grams. So now you have individual masses of each of the constituent components. Okay, and now you just need to put these values in the formula. Okay, so what was the formula? 100 multiplied with W1 divided by total mass of air into, that is percentage by mass of N2. Similarly, percentage by mass of oxygen is 100 multiplied with W2 divided by total mass of air. Similarly, W3 divided by total mass of air into 100 will give us percentage by mass of CO2. So there is a common denominator in each of the case. In each of those cases, you have a common denominator, which is total mass of air. And what is total mass of air? It is sum of mass of its components, right? If you have to calculate total mass inside a container, what you do? You sum the masses of all of the components inside the container. So basically the container has nothing but N2, O2 and CO2. So you sum these masses. Okay, basically what you have to do is you add the individual masses, 109.2 plus 33.6 plus 2.2. Once you add these masses, what you get is 145 gram is total mass of your air sample. So now you can easily calculate percentage by mass of any component. Say I want to calculate percentage by mass of oxygen. So that will be equal to 100 multiplied with given mass, let's say W2, and let's say total mass is equal to W. So answer will be 100 multiplied with 33.6 divided by 145. Okay, similarly percentage by mass of CO2 is equal to 100 multiplied with W3 divided by total mass of air, which is W. So 100 multiplied with 2.2 divided by 145. Okay, this is your percentage by mass of CO2. And similarly you can calculate percentage by mass of nitrogen. Okay, so this is how you calculate percentage composition in a given mixture. It's pretty simple. Once you practice more questions, you will see that it's a very basic concept. In fact, you don't usually get questions directly on percentage composition. You will see in the next session we'll use these percentage compositions for a different purpose. Alright, so for now let's move on to the next part of our percentage composition, which is percentage composition in a given compound. Okay, we have already calculated percentage composition in a mixture. Okay, a mixture has various components Okay, but a compound is a whole. It is an individual whole, like glucose, like carbon dioxide, like water. They are all compounds. Okay, like ammonia, again a compound. So how do we calculate percentage composition in a compound? So let's say you have to calculate percentage composition for a given element, okay, present in 1 mole of a compound. So how do we do that? Again, there can be two different percentages, percentage by mole and percentage by mass. So percentage by mole and percentage by mass are again calculated by multiplying a fraction with 100, because you have to report percentages. So you have to multiply the fraction with 100. So percentage by mole is 100 into some fraction, and percentage by mass is 100 into another fraction. So for percentage by mole, the fraction is moles of atoms of the element divided by total moles of all atoms. Let's say I have carbon dioxide, CO2. What I am talking about here is moles of atoms of a element. So CO2 has two constituting elements. One is carbon and another is oxygen. So moles of atoms of element. So let's say I want to calculate percentage by mole of carbon in carbon dioxide. So percentage by mole of carbon is 100 multiplied with moles of atoms of element, okay, which is carbon, and its mole is 1 CO2, that is C1O2. So 1 divided by total moles of all atoms. Now carbon has 1 mole, oxygen has 2 moles. So total moles is 1 plus 2, that is 3 moles. So 100 multiplied with 1 divided by 3. This gives me percentage by mole of carbon in carbon dioxide. Similarly, I can calculate percentage by mole of oxygen as 100 multiplied with 2 divided by 3. Okay. So once I have calculated both of these, what I have done is I have identified the constituent elements, which is carbon and oxygen, and I have calculated their respective molar percentages. So basically now I have complete percentage composition of CO2. Okay. Similarly, I can calculate percentage by mass, and I can calculate percentage by mass as 100 multiplied with mass of atom of an element, okay, divided by molar mass of compound. Okay, percentage by mass is calculated as 100 multiplied with mass of the element in 1 mole compound divided by molar mass of compound. Since we are talking about 1 mole compound, we have used denominator as molar mass of the compound. Okay, if we were not talking about 1 mole of compound, say 2 mole of compound, then we will calculate mass of element into 2 mole of compound divided by mass of 2 mole of compound. Okay, you can do that as well, or you can always use this formula. This formula is always valid. Okay, this formula is always valid, and let's see again with an example what I exactly mean when I am talking about these formulas. Okay, that would clear up the air a bit. So let's see. Say you have a compound glucose. Okay, we already know its molecular formula, C6H12O6. Okay, we already know the molecular formula, C6H12O6. Okay, so now I have to calculate molar composition of carbon, hydrogen and oxygen in this compound. So how do I calculate molar composition? Molar composition is 100 multiplied with moles of atom divided by total moles of all atoms. Okay, so let's see. C6H12O6, it has 6 atoms of carbon, it has 6 atoms of carbon, 12 atoms of hydrogen and again 6 atoms of oxygen. So in 1 mole compound I have 6 atoms of carbon plus 12 atoms of hydrogen plus 6 atoms of oxygen. So in all I have 24 atoms in 1 mole of this compound. Okay, in all I have 24 atoms in 1 mole of this compound. So now I have to calculate percentage by mole of carbon in this compound. So that will be 100 multiplied with, say, atoms of carbon in 1 mole compound divided by total atoms of all kind in 1 mole of compound. So in this case answer will be 100 multiplied with atoms of carbon are 6. Okay, we already seen that atoms of carbon are 6 divided by total atoms are 24. Okay, we have also seen that total number of atoms are 24. So 6 divided by 24 into 100. This will be my answer. Okay, this comes out to be 25%. So glucose has 25% by mole as carbon. Similarly, I can calculate percentage by mole of hydrogen atoms. I can calculate percentage by mole of hydrogen atoms in my compound. Again 100 number of atoms of hydrogen in 1 mole of this compound divided by total number of atoms of all kind in 1 mole of this compound. So this again will give me answer as 100 multiplied with 12 divided by 24. Okay, 1 mole of compound has 12 atoms of hydrogen and total number of atoms are same 24. So 100 multiplied with 12 divided by 24, this will come out to be 50%. Okay, and just like carbon and hydrogen, I can calculate percentage by mole of oxygen, and this will come out to be 100 into atoms of oxygen. Okay, what is atom of oxygen? 6. There are 6 atoms of oxygen in 1 mole. So 100 multiplied with 6 divided by total atom is 24. This again comes out to be 25%. So now I can directly say that molar composition of glucose is 25% oxygen, 50% hydrogen, and again 25% carbon. Alright, so this is how we calculate percentage by mole in a compound. Okay, next part is percentage by mass. Let's take the same compound so things will be a bit more clear. Let's take the same compound, that is glucose, C6H12O6. Now I have to calculate mass composition of glucose. So first I identify the constituent elements, that is carbon, hydrogen and oxygen. Second, I calculate their mass percentages in this compound. So for calculating mass percentage, let's say I want to calculate mass percent of carbon. So what I do is percentage by mass of carbon in my compound is equal to 100 multiplied with mass of carbon in 1 mole of compound divided by mass of 1 mole compound, that is gram molar mass. Mass of 1 mole compound is nothing but gram molar mass. So 100 multiplied with mass of carbon in 1 mole of compound divided by gram molar mass. Similarly, percentage by mass of hydrogen will be 100 into mass of hydrogen in 1 mole compound, that is say W2, divided by gram molar mass of compound. And similarly for oxygen. So basically first you need to calculate gram molar mass of the compound, and you also need to calculate W1, W2 and W3, that is individual masses of each of the constituent elements in 1 mole of compound. So I have carbon. So mass of carbon in this compound, 1 mole of this compound is, there are 6 atoms. So 6 into mass of 1 mole is 12. Okay, 1 mole carbon weighs 12 gram. So 6 multiplied by 12, that is 72 gram. Similarly, W2 is equal to, there are 12 atoms of hydrogen and 1 mole atom of hydrogen weigh 1 gram. So 12 into 1, that is 12 gram. And W3, so there are 6 atoms of oxygen and 1 mole atoms of 6 mole atom of oxygen and 1 mole atom of oxygen weighs 16 gram. So 6 mole will weigh 96 gram. So in all I have 72 gram carbon, 12 gram hydrogen and 96 gram oxygen combining together to form 1 mole of glucose. And what is the gram molar mass of glucose? Gram molar mass of glucose is nothing but sum of these individual masses, 72 plus 12 plus 96. Okay, we already know how to calculate gram molar mass. So when you sum 72 plus 12 plus 96, the answer will come out to be 180 gram. Okay, and we know 180 gram is mass of 1 mole of glucose. So I can write gram molar mass as 180 gram per mole. So now I just need to substitute the values. So percentage by mass of carbon is 100 multiplied with mass of carbon in the compound, that is 72 gram, divided by total mass of the compound, which is 180. Okay. Similarly, I can calculate percentage by mass of oxygen and percentage by mass of hydrogen. Let's say I first want to calculate percentage by mass of hydrogen. So it would be mass of hydrogen in 1 mole compound divided by mass of 1 mole compound multiplied with 100. Again we are multiplying 100 only because we have to calculate percentages. So answer is 100 into, okay, total mass of hydrogen is 12 gram. Okay, all the hydrogen atoms together here weigh 12 gram, divided by total mass of 1 mole compound 180 gram. And lastly, percentage by mass of oxygen, okay, is equal to 100 multiplied with mass of oxygen divided by total mass of compound. Okay, and this will come out to be 100 into 96 by 180. Okay. And you can calculate this, you can solve this for fractions and calculate your final answer. Alright, what will be the final answer? Let's say if you want to calculate for hydrogen, those calculations are relatively simpler. Let's calculate for hydrogen. So 12 by 180 into 100, this will come out to be around 6.67. okay, after rounding up 6.67 percentage. So you have to use this percentage sign after your number, after your answer, because you have calculated percentages. So you have to use the percentage sign after your answer. Okay, similarly I can calculate for carbon. For carbon it will come out to be 72 divided by 180 is, okay, around 0.4. So this will come out to be 40%. Okay, like this. So you have to report final answer using percentage symbols. So this answers covers all of the topic of percentage composition. Okay, now remember one thing. See, percentage composition is a common term. Alright, you have to use it throughout the chemistry, okay, and not just physical chemistry. And even in physics you might need to use percentage compositions. Okay, so the basic concepts, the basic the basic phenomena behind the term percentage composition is same everywhere. We just tweaked it a bit for different cases, like for in compound or in a mixture or some other place which you might come across later on. Alright, so that's it for percentage composition, and until next time, and in the next session we'll start with empirical formula. Okay, again a new topic in our mole concept chapter. So until then, and once again, thanks for watching Edupedia World videos.